All right, the equilibrium constant Kc can be expressed as the concentration of the product raised by the power in the of the coefficient in the balance equation. Same thing over the concentration of reactant raised by the power of the coefficient. Okay, so the product and the reactant. And C stands for concentration. I'll give you some examples. So N2O4 go to in equilibrium with 2NO2. So the Kc can be expressed as the concentration of NO2 square over the concentration of N2O4 to the first. So there's 1, just put 1 as a power. Okay, all right, super simple. Can you make the Kc for these two equations? Right, pause the video, do by yourself first, and check with me. Again, so concentration of product over concentration of reactant. So first of all, we have NH3 square, ammonia square. This is ammonia. Over concentration of nitrogen gas times concentration of hydrogen gas to the cube. Okay. Last one at the bottom. So we got what we got. Product. So C4H9 or CH3 MTBBE. Concentration of it, and concentration of water. And at the bottom, we have methanol and C4H9OH. So that's butanol. Yeah, butanol. Okay. All right. Now, let's focus on the quantitative side of Kc, equilibrium constant. Okay. We can talk about the position of equilibrium, which is what chemists are interested in. So if the Kc of this this equilibrium N2O4 to 2NO2 is 4.64 times 10 to the negative third, I can write as this, right? So concentration of NO2 square over N2O4, that's a Kc. I can rewrite this 4.64 times 10 to the negative third as that over 1. That number over 1. So which means that at equilibrium, the most of the species that exist in the reaction flask favor N2O4. That because N2O4 is 1,000 times bigger number than 4.64 times 10 to the negative third. So they are N2O4 about 1,000 times more than NO2. In this case, this equilibrium favor the formation of the reactant because there are more reactant in equilibrium. Okay, so these are relative number. So it's not like one at equilibrium we have only one molecule of N2O4 and not even a fraction of molecule in NO2. No, that's not what it means. This fraction means that these numbers are relative, right? So it means that at equilibrium they are N2O4 about 1,000 times more than the amount of NO2. That's it. Okay. All right. Try one more time. So hydrochloric acid dissociate in water to make hydronium ion and chloride ion. Right. You can write Ka. So we do Ka. Same thing with Kc, but A stands for acid because hydrochloric acid is an acid. Yeah, you will see a lot of Ka in the next chapter, chapter 13, acids and bases. Okay. Anyway, so Kc, Ka, same thing. So Ka equal to the concentration of the product over concentration of reactant, and that's the number. Okay, so 10 to the 7, that's 10 millions, which means that in equilibrium, this equilibrium favor the formation of the product about 10 million times over the concentration of the reactant. Okay, so that's why this reaction go forward, a lot forward, right? The top reaction go backward to the reactant. All right, so let's say at equilibrium, the concentration of NO2 is that. Hydrogen gas is that, and concentration of ammonia is that, molar, right? Molarity. Calculate the equilibrium constant at the temperature. So first off, let's start with express Kc of this equilibrium first. All right. So same thing, Kc, the concentration of the product. Yes. So square over the concentration of reactant. So cube for the hydrogen gas. All right. Now just plug in NH3 square. So NH3 is 1.6 times 10 to the negative second. Square. There's a square right there. Watch out. N2, so 3 times 10 to the negative second molar. And hydrogen gas, 3.7 times 10 to the negative second cube. All right. Do the math right here. So watch out how you type the calculator. Some people type the calculator wrong and just get the wrong answer. You should get 1.7 times 10 to the second. All right. Now, 1.7 times 10 to the second. So is it favor the product or reactant? So I can rewrite it as 1.7 times 10 to the second over 1. Totally, at equilibrium, this equilibrium favor the formation of ammonia over N2 and H2. So about 170 times over 1. Okay, so favor the product. All right, so Kc is for solution, so concentration, right? We use Kp for gas. Let's take a look at on the next video.